Okay, so this is lecture 5.2 and 6.1. So we are going to finish chapter 5 and we're going also to start chapter 6 in this lecture. Okay, so if you remember, on chapter 5 and the previous lecture we started to talk about applications of group theory. Specifically we started to talk about the splitting of atomic orbitals in a crystal potential, and we are going to continue this chapter now. And first of all, I'd like to do an example to solve problem 5.3 of the textbook. This is problem 5.3. Show that the D level for a transition metal impurity in a metal cluster with IH symmetry, so with icosahedral symmetry, it's not split by the icosahedral field. So this is similar to what we did in the previous lecture when we considered a D level impurity in a cubic symmetry, O group, the O group. Now we are going to consider the IH group, which is a higher symmetry group. It has 120 symmetry elements, and we are going to show that in this case, contrary to what we've seen in the last lecture, in this particular case, the D level is not split by the reducing the symmetry from the full rotation to icosahedral. Okay, so to do that, we're going to remember this formula that we discussed last time. Sorry. We're going to discuss, we're going to start with the formula for the characters of the full rotation group under a rotation by an angle alpha. And this is a relation that we shown last time. The reducible representation of the full rotation group, it has the angular momentum quantum number L, and the character is written as the sine L plus 1/2 alpha divided by sine of alpha over 2. So this is the remember the character for rotation over an axis by an angle alpha. Okay, so let's write here then for the different classes of the group, the characters for the representation gamma L, in this case L equals to 2, right? So this is the same that we considered in the last time. And for instance, for the identity, we have seen that already. This is equal to 5 because it's the degeneracy of the D levels. And other results that we have seen already last time were that when we do a rotation by 2 pi over 3, when alpha equals to 2 pi over 3, we have seen that, and L equals to 2 and alpha is 2 pi over 3. We have calculated this last time, and this is equal to -1. And if you have a pi rotation, C2 axis, this is equal to 1. Okay, so we know already that this is -1, this is 1. Okay, now let's consider the C5 class. For the C5 class, we need to, so for the 12 C5, we need to consider alpha is equal to 2 pi over 5, right? So the character is equal to the sine of 2 pi over 5. When I have it's 5 over 2 times alpha times 2 pi over 5, this gives me pi, sine of pi divided by sine of pi over 5, but it doesn't matter because the sine of pi is 0, so this is 0. Okay, so this character here is 0, and now I have C5 square, so this other class 12 C5 square, which is twice C5. So instead of rotating by 2 pi over 5, you rotate by alpha equals to 4 pi over 5. And the result for the character is the sine of 2 pi now, which is also 0, divided by sine of 2 pi over 5, right? This is 0. So this character is also 0. Okay? So what about the remaining columns? So we learned last time that for the identity, the character for the identity operation or the identity class was simply minus 1 to the L times 2L plus 1. Okay? Since in this case L equals to 2, so this is an even number, so this is simply 5. So for the inversion, sorry, not identity, for the inversion symmetry, we have 5 here. Okay, now we have other symmetries here, improper rotations and reflections, and if you remember last time I told you that we're going to deal with that in the next chapter, how to obtain that. But what I can anticipate to you is that this group IH, we're going to see actually this today, this group IH is a direct product of icosahedral group, probably the group I think, times the inversion. What that means is that if you think, you can divide the character table in different blocks, in 4 different blocks. So this block would basically give you the character table for this a smaller group, with the I group, not IH, the I group. It's also an icosahedral group, but it's not the IH, it's the I group. This second block here, it's constructed, the other blocks are constructed by making combinations of the symmetry operations of the I group, which are those ones, only identity and rotation, and I combine those with inversion. So E times inversion is inversion. C5 times combined with inversion is a S10 operation, and so on and so forth. And C2 combined with inversion is a sigma, is a reflection. Okay? And from that you can construct the character table simply by multiplying. Then you have you have twice the number of irreducible representations. They are characterized by letters G if they are even under inversion, or U if they are odd under inversion. Okay, and you notice that for the even representations, you basically repeat the characters here. You take the characters for the rotations, and you use the same characters here for the operations that you combine with inversion. But for the odd representations, you multiply them by -1, okay, when you combine with inversion. So what I'm trying to say is that in this case, since we have an even representation, because L is equal to 2, so all these states are even under inversion, I will anticipate to you basically that the characters here are the same. 0, 0, -1, +1 for these other symmetry operations. Okay. All right. So these are the characters for this particular representation of the full rotation group, and what we want to know is to see how they decompose when you lower the symmetry to IH. So I could actually start doing this decomposition, but by inspection you can already see that this is essentially equal to the HG representation. It's a five-fold representation, five-dimensional representation, and it's even under inversion. You can see that the characters are essentially the same. So basically what this is saying is that when you have well, in the end, basically what this is saying is that the gamma 2 rotation for the IH group is essentially the HG representation. So the five-fold degenerate D levels in an atom, they are not split by icosahedral group. They remain five-fold degenerate. And another way to see that is by looking at the basis functions. So if you remember, the basis functions for D states, for D orbitals, you can express, you can rewrite spherical harmonics in real form as a linear combination of spherical harmonics. You can rewrite them in Cartesian coordinates, and when you do that, you have something that are precisely those combinations of quadratic functions. Okay, xy, xz, yz, x square minus y square, and 2z square minus x square minus y square. So if you don't know that, I mean, you're gonna see that many times. These are precisely the shapes of the five different d orbitals in Cartesian coordinates. Okay, so by looking at this five different basis functions and identifying them with the 5d orbitals, it's another way to right away understand that the d states are not split by the icosahedral field. Okay, so very good. So this is the 5.3 exercise or problem. So let's go ahead now and let's comment a little bit more on basis functions. So we discussed last time that group theory would not tell us which level it's lower energy when you have a splitting. So group theory tells us precisely what are the degeneracies that you get after a crystal field splitting, but it doesn't tell us which level is lower and which level is higher in energy. So this is the example we did last time. We had a D state under a cubic crystal field, and we saw that for this particular case, we saw that the originally five-fold degenerate level would split into a three-fold and a two-fold level with T2 and E symmetries, but we don't know which one is lower in energy. So what I'm going to discuss now is that in some cases, using some simple reasoning and looking at the shapes, the geometrical shapes of the basis functions, it's possible to infer which level is going to be lower in energy. So, and let's use this precise situation as an example for that. So in this case, these are the basis functions that we get. For the threefold degenerate T2 level, we have xy, yz, and zx as the three basis functions. And for the twofold degenerate E level, you get this combination of two functions. The two partners are x squared minus y squared and 3z squared minus r squared. Okay. All right. So if you look then at the shapes and you combine this with the information, let's say, just for the sake of argument, let's say that we have an ionic crystal and the central impurities is a cation, so it substitutes one of the cations of the ionic crystal, and the first neighbors are anions. Okay, so these are the 6 first neighbors, they form an octahedral, and let's say they are anions. Also, let's say we have negative charges, okay, around the positive impurity. Okay. So now let's look at the geometrical shapes of the orbitals or basis functions. So for the T2 level, we have functions like xy. This is the xy orbital. So it's positive here, negative here, and it has this shape. Okay, it doesn't matter the sign, because when you square the wave function to get the probability density of electrons, what you can say basically is that you have high probability of finding electrons along these diagonals, but you have low probability of finding electrons along the Cartesian coordinates, for instance along x or along y. And these are precisely the directions where we have the anions, okay, the negative ions that I represent here. So when I see that, then if I remember that electron has a negative charge, that means the energy, the interaction energy between this orbital and these negative charges are not going to be very high, because the electron cloud is not pointing towards the ions. All right. This is the same argument I could use for the YZ and for the ZX basis functions. It's essentially the same argument. Now, if we look now at the E symmetry, so we have these two functions, x squared minus y squared and 3z squared minus r squared, and essentially you can see that they have the opposite situations that we had here. So they are actually the electron clouds are pointing in the direction of the negative ions. So this increased the interaction energy between electron and the crystal field, which is positive, right? Because it's a repulsion between negative charges, the negative clouds of electrons and the negative point charges of ions. So that means for that these E states, they should be higher in energy, because you have a more repulsive interaction between the electrons and the charges. they should be higher in energy than the T2 level. Okay? So this is the conclusion. So this is just an illustration. You're probably going to work a little bit with that in the problem set. But it's just an illustration on how you can sometimes use the shapes of the basis functions and try to get an idea which level is higher in energy when you have a crystal field splitting. Okay? All right, very good. So the last topic in this chapter is a comment about crystal fields in general. So the shapes of crystal fields and the symmetries of crystal fields. So the crystal potential is a totally symmetric function. What that means is that for any, and again, here I'm using the cubic symmetry OH group as an example. For any of the symmetry operations of the group, when I apply some symmetry operation, the crystal potential field, it's invariant. Okay? So this is the same as saying that the crystal potential transforms like the identity representation, which is in this case A1G, with all characters equal to 1. So that basically means, in other words, that we can use this function. Oops. This means that we can use this function V crystal, which is a very complicated function of x, y, and z, but we can use this as a basis. This is a basis for the representation A1G, right? Because essentially it's a function that goes into itself for any symmetry operation of the group. Okay? So using the notation that we have developed in this chapter, we can, in other words, write V crystal, this very complicated function of x, y, and z, as a basis function of A1G. So I can write using this state vector notation. Okay? It's one possible basis function for A1G. All right. So, but we also know that spherical harmonics are a complete basis. Okay? We probably learned that in quantum mechanics. It's a complete basis set. It's a complete basis. So that means that I can expand any function, even V crystal, I can expand any function as a linear combination of spherical harmonics with some coefficients ALM and YLM, theta and phi. I'm expanding the angular dependence of the crystal potential as a linear combination of spherical harmonics. Okay? All right, so very good. But in the previous lecture, we learned how to decompose spherical harmonics in terms of the irreducible representations of the group, right? So we just did that one more time. So we know that on the other hand, I can write any spherical harmonic as a linear combination for all representations gamma j and all partners k with some proper coefficients. We'll call them a, l, m, j, k, for instance, of the basis functions of any group gamma, j, k. So we learned how to do this decomposition in the previous lecture. Okay, so we also know that the basis functions are orthogonal. Okay, so actually we're gonna show this result in this lecture one more time, but we know this from analogy. We know this from analogy to quantum mechanics, right? From the analogy to quantum mechanics, we can essentially say that the basis functions are orthogonal. So unless we have the same representation and the same partner, I have 0, otherwise I have 1 for this scalar product. Okay, so but then let's again look at this problem in this particular case, when we know that V crystal transforms, or V crystal is a basis for the A1G representation. Okay, so and if you look at this expansion now, and we try to see which terms, which components Lm are going to be in the expansion of V crystal in spherical harmonics. By looking at these two results, we can essentially see that this V crystal, if you take this scalar product, this is going to be different from 0 only if ALM for A1G is different from 0. So only if the expansion, because when I do this scalar product, I am basically doing this, right? So unless I have in the expansion of spherical harmonics a term, unless A1G is part of the expansion for a different for a given spherical harmonic in the basis functions of the group, so only if the A1G representation is contained in the expansion of the spherical harmonics, then this spherical harmonic is going to be also part of the expansion of the crystal potential in this expression. I hope this is clear. But in any case, just by looking at this table, you can see that for different values of L, these are the different decompositions of spherical harmonics into different irreducible representations of the OH group. So what this table means is this equation for different values of L. Okay. So and what the converse of that is the following: only those representations in which A1G is present, like L equals to 0, L equals to 4, L equals to 6, 8, etc. Only those spherical harmonics are going to be present in the expansion of the crystal potential. So using group theory, you can anticipate some results about the expansion of the crystal potential in terms of spherical harmonics. For instance, you can see that in this case, if you remember now that the angular momentum quantum number has to do with the exponents in Cartesian coordinates. So this is xyz to the 0 power. So this is linear in xyz. This is quadratic in xyz, third power, fourth power. You can see that after the constant term, you don't have a quadratic. Or first of all, you don't have any of the odd values of L in this expansion, and this is reasonable because the cubic crystal is even under inversion. But you also don't have some of the even values as well. For instance, you don't have L equals to 2. The smallest value of L after L equals to 0 is L equals to 4. Okay, so that means that I must have something like x to the 4th or y to the 4th power, something like that, in the expansion of the crystal potential. So let's try to verify that. Using again this system. So let's suppose I have this is my origin, okay, and near the origin I want to see how let's take positive charges. Let's see, plus E at these positions, and I want to see how I can expand the electrostatic potential near the origin from the influence of these 6 different point charges. Okay, so I want to see how the V crystal of X, Y, and Z behaves near R equals to 0, near the origin. Okay, and let's expand this in a power expansion. So I have then to sum. The contributions of electrostatic potential for these 6 different charges. Okay, so let's look at one of them individually first. Let's look at the contribution from the charge at x equals to minus a. So let's say this is 2a. So I have point charges at x equal to plus or minus a, y equals to plus or minus a, and z equals to plus or minus a. Okay. So let's look first at the contribution to the potential from the x equal to minus a charge. So essentially I have to, let's use CGS units here. I have to calculate this quantity where R prime is essentially R plus AX, right? Okay, so what I'm doing is I have this. I want to calculate the potential at the point R from the contribution from a charge located at minus x, ax hat. So I basically have to, this is my R prime. Okay. All right. So this is equal to E divided by the square root of x plus a square plus y square plus z square. Okay, and I can write this. This is equal to e over a times 1 over square root of 1 plus x over a square plus y over a square plus z over a square. Okay, and now I can do an expansion for small values of x, y, z. So expansion near the origin, and I can use this well-known result. 1 plus epsilon to the minus 1/2 is equal to 1 minus 1/2 of epsilon plus 3/8 epsilon square minus 5 over 16 epsilon third plus 35 over 128 epsilon fourth plus higher order terms. Okay, so so let's make a long story short. You can check those calculations, but if I now combine the contribution from x at minus a with the contribution of from x equals to 8, and you can check this expression is correct, I get 2e over a one minus 1/2 r2 divided by a2 plus 3/2 x squared divided by a square plus fourth order term minus 15 over 4, and then I have x squared over a square times r squared over a square. This is also fourth order term plus 35 over 8 x squared over x to the fourth divided by a to the fourth plus higher order terms. Okay, this is I'm basically copying this from the book. So now this is only the contributions for the from the charges at along the x-axis. If I do the same along the y and z-axis, so you can already see, I think that's the point I want to make. When you do the same for y and z, I'm going to have y square and z square over a square here, and this is going to cancel this term here. Okay, and so the bottom line is that the quadratic term is going to cancel, and essentially I can write down at the end of the day, I will be able to write down the V total, which is the total crystal field near the origin, as 2e over a, and then I will have here a constant term, in this case it's 3, plus, which is this constant term comes from this L equals to 0 contribution, right? The contribution from L equals to 0, this constant, plus the next term that survives is 35 divided by 8a to the fourth, and have here x to the 4 plus y to the 4 plus z to the 4. And there's another fourth order term here, which is minus 21 over 8 r to the fourth divided by a to the fourth. Okay? Plus higher order terms. So the bottom line is, with this specific and simple example for a cubic system, I basically I have the same result as I had predicted from group theory. Okay, so I don't have quadratic terms in the expansion of the crystal field potential, and from group theory this could be anticipated by essentially looking at which angular momentum representations of the full rotation group can be decomposed, or they all can be decomposed in different linear combinations of irreducible representations of the group, but only those that contain the identity representation A1G will contribute to the crystal potential. And the reason for that is that the crystal potential is a totally symmetric function, and it transforms like the A1G representation. Okay, so this is also a very powerful result that we get from group theory. Okay, so this finishes chapter 5, and this is a problem set for chapter 5, which has only one problem, problem 5.2. And for this reason, and also because chapter 5 and chapter 6 are smaller chapters, for this reason I will ask you to return this problem set next Monday. Okay, so we have like 5 days to do this problem, and also for this reason I will start now chapter 6, and I will finish chapter 6 next lecture on Monday. Okay, very good. So chapter 6 is another application of group theory, and in this case it is an application to selection rules of, for instance, of different transitions. So one of the possible applications of selection rules is looking at selection rules of different optical transitions between, for instance, levels in atoms or molecules. So, and this is before we do this, we need to study the concept of direct products, and this is what we're going to start today. So the typical problem, as I said, is that I have a certain quantum system in which I have, for instance, a perturbation H prime, and this perturbation can be, for instance, the perturbation from an electromagnetic field if I have an atomic system, for instance, and I want to study if this perturbation will be able to promote optical transitions from one level to another level, and I can use group theory to tell me that just by looking at the symmetries of the initial and final state. So in the end of the day, I will need to look into transition matrix elements such as this, when alpha and beta are, for instance, initial and final states for a certain optical transition, and H is some perturbation Hamiltonian, for instance, due to the light, the electromagnetic Hamiltonian. And we want to know if this will vanish by symmetry or not. That means if the transition will be allowed or forbidden by group theory. So this is a very important and powerful application of group theory. Okay, so this is what we will learn by the end of this chapter. So again, this is the typical and perhaps the most important example of selection rules, but we are going to see other types of selection rules in this course. But this was one of the most important of them, the electromagnetic interaction as a perturbation. So this is probably, you have seen that in quantum mechanics or in electromagnetism courses. But if you write this is again in Gaussian units, but if you write the effects of an electromagnetic field in a Hamiltonian of a quantum system, you have this term which involves, so this is not in the denominator, right? It's in the numerator, which involves the vector potential A, and you can expand that. And if you take the linear term in A, in the spirit of perturbation theory, this term, if the field is small, this term is going to be more important. And you can write your perturbation. This is your unperturbed Hamiltonian, H0, and this is your perturbation that is linear in A and the momentum P. Okay, this is the Hamiltonian of the electromagnetic field. So this is a typical example that we're going to see in this chapter. So, and okay, so before we get there, we need to develop a few concepts going back to the formalism of group theory. And the first concept we need to develop here is it's about the orthogonality of basis functions, which we have already used. We just used that, if you remember. But if you remember, we have used that in analogy to quantum mechanics. But now we're going to do a formal proof of orthogonality between different basis functions, which is basically we will prove this theorem. The theorem is that two basis functions which belong either to different irreducible representations or to different columns or rows of the same representations, meaning different partners, they are orthogonal. Okay, let's prove this theorem. So let's consider that we have two basis functions that I will call phi alpha I and psi alpha prime I prime as basis functions I prime as basis functions of representations gamma I in this case and gamma I prime. In the other case, and this is the partner alpha. So this is this vector, and this is a partner alpha prime. So let's prove that they are orthogonal unless I equals to I prime and alpha equals to alpha prime. Okay? So let's do this by looking at the effect of applying the same symmetry operation P of R onto phi alpha I And as we have seen, this can be written as a linear combination from j equals to 1 to Lj. Lj is the dimensionality of the gamma I representation. And here I have the matrices, matrix elements alpha j. These are a linear combination of all other partners of these representations that I will call phi I. Let me use this function notation instead of basis vector notation, just for now. Okay? Alright. And I can also apply the same symmetry operation to psi. Let's apply the same symmetry operation to psi alpha prime I prime. This is equal to sum for j prime to Li prime d I prime of r, and this is alpha prime j prime psi all the other partners psi j prime of representation I prime. All right. Okay. Now this is a crucial point. Let me calculate now the scalar product between those two basis functions. Let me calculate this scalar product. And the bottom line is that this is a number. And a number is invariant. It doesn't depend on a particular coordinate system that I use. So if I apply any symmetry operation to phi or to psi and calculate this number again, this should be exactly the same number. It should not change. It should be invariant, right? So the bottom line is that this is equal to the same number when I apply a symmetry operation R on this function, and the same symmetry operation P of R on this other function. Okay, should be the same. All right. Okay, so let's then calculate this. Let's calculate this and just substitute these two expressions here in the scalar product, and the result is a double sum of j prime and d I of r alpha j and complex conjugate, and d of I prime alpha prime j prime, and the original scalar product. Okay. Now, all right. So this is for symmetry operation R. Now, if this is all the same number, no matter which symmetry operation R I choose, so I can also sum over all symmetry operations of the group and divide by the number of elements in the group, and then it's going to remain the same number. So I can do this. I can say this is equal to 1 over h, and I can sum over r. Okay, so I have a sum over j prime, and I can sum over r, and you may have already seen where this is leading us. This is leading us to the wonderful orthogonality theorem once again. All right. So again, using the wonderful orthogonality theorem, we know that this is equal to 1 over L, sorry. This is 1 over Lj, a bunch of deltas. So delta I prime, delta j prime, and delta alpha prime. So this is equal to 1 over Li delta I prime delta alpha prime. Okay, and a sum of there's also this sum over j. So this is a number that it really doesn't matter much, because I just want to see if this is 0 or non-zero. Psi j, sorry. Okay, this doesn't matter, but what's important here are this delta function. So this number is only going to be different than from 0 when I have the same representation, I equals to I prime, and the same partner, same row or same column, right? Alpha equals to alpha prime. So this is the proof of a result that we have been using actually so far, but this is the rigorous proof of that. Okay? So this is the first thing I wanted to show. And the second thing I wanted to discuss is the concept of direct product of two groups. The direct product group. So the idea is, let's consider that I have two groups. A group that I call GA, which has some elements identity, A2, A3, etc. until age, let's call it age A, the dimensionality of the group A. And let's suppose that I have another group, GB, which has elements E, B2, B3, etc. until the last one, which is B, HB. HB is the dimensionality of group B. Okay? What I define by the direct product group, and I use the notation GA direct product with GB, is the so the other condition I must have is that all elements in A commute with all elements in B. In GA, sorry. All elements in GA commute with all elements in BG, in GB. So the AI and BJ commutator is equal to 0. Okay? So if that's the case, I can construct the direct product group simply by multiplying all the elements of the group by all the elements of the other group. So if I multiply the elements of group GA by the identity, I get the elements of group GA. So A, A2, etc. until AHA. Now I multiply all the elements of GA by B2, so the next element is identity times B2, which is B2. Then I have A2, B2, and then etc. And I keep doing this until the last one, which is AHA times BHB. Okay? So this is a group. We haven't shown that, but it's easy to show that this is a group, which is the direct product group. And the number of elements, this is a group with order. The order of the group is HA times HB. Okay. Okay. So we have already seen some simple examples of these direct product groups, and common examples involve direct product of any group, any point group with the inversion group. So this is a common example. The inversion group that has many notations. Sometimes we use CI, or sometimes we use S2, or sometimes for short we just use the symbol I. But this is, be careful so that you don't make confusion with the operation I. This is a notation for the group, and the group CI is composed of two elements only, the identity and the inversion. Okay, this is the inversion group. There's also a group of reflections. For short, let me call it a reflection group. And again, there are a few notations. Sometimes we call C sigma or C1G. So sometimes we just for short call it just sigma G. And the group is, again, has only two elements, the identity and the sigma H operation, horizontal reflection. Okay? And we've seen examples of these. Actually, you may have seen this in character tables. For instance, the group D3D, which we have used many times already in problems, can be seen or can be written as the direct product between group D3 and the inversion group I or CI. So that basically means that if I, for instance, if I look at the stereograms of group D3, this is the stereogram of group D3, and if I now add inversion, you can essentially see this guy, the upper atom here. If I add inversion, goes to the lower atom here. This guy goes to here, and if I keep doing all the possible inversions, you will notice that I get precisely the D3D group. So another way to see that is by looking at the character table, as I have already discussed today for the IH group. So if you look at the character table for group D3D, you can see that we can split the character table in 4 different parts, starting from the group D3. So this is the character table of group D3. Sorry. This is the character table of group D3. Now you add the inversion group. So you make the direct product with the inversion group, which has 2 operations, identity and inversion. So first here you apply the identity and all characters are the same, and then you apply the inversion, and for the even operations you repeat the characters here, and for the odd under inversion, sorry, not operations, for representations, there are even under inversion and odd under inversion representations. And to get the characters of those, starting from the character of the D3 group, for the even representations, when you add the other symmetry operations, you repeat the characters, and for the other representations you multiply by a minus sign. So we're gonna see this next lecture, but the idea is that you see that all the 3 extra rows here, they are basically combinations of these other 3 symmetry operations. Sorry, the 3 extra columns. The 3 extra columns are combinations of all these 3 symmetry operations with the inversion. So E times the inversion, sorry, E times the inversion is inversion. Okay? Now inversion times C3 and inversion times C2. When we have inversion multiplied by C3, is typically an S, an improper rotation. It's an S operation. And you have inversion multiplied by C2 prime is typically a sigma, is a reflection operation. Okay? So this is the character table of the D3D group, and now you understand how one can see the D3D group as a direct product of the D3 and the inversion group. So that's why we have this notation that we may have seen it already. So in the character tables that you have in the appendix of the book, you will see many times different point groups written as direct products between smaller groups and inversion, or the direct product with the reflection group. Okay, this is very common. Okay. So this is the idea of the direct product of 2 groups, and we will continue on Monday on chapter 6. So this is the end of this lecture today. Thank you.